Okay, so we're going to continue on. So when we last left here, like 2 minutes ago, we were talking about these different orbitals and uh, where they are in terms of energy levels and what orbitals are on each energy level. Again, as I mentioned in class there, as we finished up the last one, really all the sort of availability of orbitals and all that is based on what are known as the sort of the four quantum numbers. And we kind of touched upon three of them there, and we'll actually hit the other one. But they are N, L, M sub L, and M sub S. As we've been talking about, N is really the one for our class that you should focus on. When you get to 1A, you'll talk about the other ones. But N, as we've been talking about, basically, again, is the energy levels. L is really the type of orbitals, as we went through a couple of those calculations there at the end, that tells you on those particular energy levels what orbitals are sort of available to you. So like there are S's, P's, and stuff like that. So again, as we did the calculation, for example, for the N equals 1, uh, the only possible one that we talked about being for L was 0. And again, a 0 at that point represents an S orbital. And that's why we don't see any other orbitals available on the first energy level and so forth. M sub L is a little bit more complicated, but ultimately you could think of it as it will tell you how many orbitals there are for those particular subshells. So, for example, here with the P, they have three numbers. Each of those three numbers represents one individual P orbital. And that's what we were talking about here at the very end, where we did like the L is equal to 4. And then we had 9 different numbers there for the -4 to +4. And that would represent, again, basically 9 different like g orbitals. And again, each one could hold 2, which is the 18 electrons. So if you just think about the sort of number difference between the n equals 3, where we have basically 3 squared times 2, which is our 18, to our n is equal to 4, which would be 4 squared times 2, which is 16 times 2, which is 32 electrons on that energy level. To now we get to our n equals 5, which is 5 squared times 2, which is 25 times 2, which is 50 electrons, right? So the difference between 50 and 32 is those 18 electrons that now can technically go into those 9 orbitals that we just talked about at the end there, those g orbitals. And that's why we have, as I think was the question, why when we go to like the next level, is there more electrons sort of available? And again, technically there's more orbitals available, again, not being used, but that's where, again, the difference in the number of electrons come as you continue up to like n equals 6, n equals 7, and so forth. Again, like I said before, pretty much any chemistry class you take, based on the periodic table, you're going to max out. You're not going to go past the F orbitals in terms of needing them. And that's why we really don't talk about what comes after those in most cases, because at this point, we don't really need them to do anything with electron configuration, stuff like that. Any questions again on that there? Once again, you don't have to do any of that sort of quantum numbers other than knowing what n is. So as we were talking about as well towards the end there, when we do look at like hydrogen and all the energy of these orbitals, they are equal to each other. Again, all the orbitals on the third is equal, all the ones on the 2 energy level is equal. But when we start to get a lot more electrons involved, there's actually a shift of energy that occurs between the different orbitals. And that's because if you can just imagine, when you put more electrons in an atom, electrons are negatively charged, right? And when you put a bunch of them into an atom, do they really want to be near each other? They don't, because they have the same charge. So they try to get away from each other, but they can't, right? Because they're kind of attached to the nucleus through that wave-like function. But they will try to spread out. So what that ends up doing is it actually moves the energy level of these different orbitals that we've been talking about. And that also affects how electrons are basically put into the atom. And they're put into the atom lowest energy first. So they would go from, the 1s up to the 2s, and then our 2p, our 3s, our 3p. And again, if necessary, they will keep going. And here's really where this really comes into effect. The actual 4s orbitals actually end up being lower in energy than the 3d orbitals. So if you were to get up to, say, the 4s or after the 3p, the next set of electrons actually would go into the 4s. And once those are filled, then they would start filling actually the 3d orbitals. And that pattern follows. You can see here the 5s is actually lower in energy than the 4d. So the 5s would actually get electrons first, and then it would go into the 4d. So it doesn't go when you're writing, as we'll be talking about here in a second, electron configuration, it doesn't go in like order. So all the ones don't go together, all the twos, all the threes, and it doesn't go in that order. At some point, there is some differences in how the electrons go in. And when we write electron configuration, like we'll talk about here, we always write it based on filling order, and that's how the electrons go into the atom. And in that case, this is the proper sort of filling order. And most chemistry classes you take, this should be the order that you follow. So how do you know that order? Well, to write electron configuration, you want to be able to make a chart like this, and you could actually make this chart yourself really easily. And we always start up here, by the way, and you follow the arrows. And when you get down here, you just zigzag back and kind of keep following the arrows till you get down to here, and then you zigzag back. And you keep basically following that order. And you can see here, we go from the 3p into the 4s and then the 3d. So again, it will give you that sort of correct order if you make this. How can you make this yourself on the piece of paper? Well, all you have to remember is, as we talked about, where do all these orbitals start, on what energy level? So if you remember, on the very first energy level, we had our s orbital, right? And it wasn't until we got to the second energy level that p orbitals happened. So you come down to the right a little bit and write 2p. It wasn't until the third energy level that the D started. So you come down to the right, write a 3D. And it wasn't until the fourth energy level that the F orbitals start. Once you got that sort of arrangement of 1, 2, 3, and 4, all you have to essentially do is just fill in numbers to 7 below it, basically, and put the same letter. So if I were to do that, I would go like a 2P, or get the right letter there, a 2S, a 3S, a 4S, a 5S, a 6S, a 7S. I would come here 2P, 3P, 4P, 5P, 6P, 7P. Here 3D, 4D, 5D, 6D, and 4F, 5F. And now I've just recreated that myself with little problem. All I had to remember is 1, 2, 3, 4. And now I have my ohm chart that basically will give me the proper order as to how electrons are filled in there. So just kind of go 1, 2, 3, 4, and then just fill in the numbers down. If you go to 7 or so with the D and the F, it's not going to make a big difference because you'll never get there in most cases. But they again do stop actually at 6 and 5 for the D and the F. But even if you put an extra number down there below the 6D, you probably won't get there anyways in whatever you're writing. So you'll still be in okay order. Yeah.
So, like, when, because I know you said when there's too many electrons, it kind of shifts the levels of energy.
Yeah.
So is there like a certain number?
Pretty much anything outside of hydrogen. So anything with more than one electron, this is the order. And hydrogen follows here too because it just has one anyway. So it's just at the beginning to start anyway. So yeah, so pretty much all uh, all elements pretty much will follow this in terms of filling. Again, hydrogen's energy levels are still the same because it really has this one electron, but it only gets to the first guy anyway. So pretty much after that, then you want to follow this. So pretty much for everybody. So the reason this is important is if you know this and are how to make this on your paper, and you know what we talked about before, that if you filled up the s orbitals, that's going to max out at 2 electrons. If you filled up the p subshell, you're going to max out at 6 electrons. And if you fill the d subshell, that's 10 electrons. And our f subshell, which is 14 electrons, you will be able to write any electron configuration you need to write pretty much. So if you know basically those two things, you should be able to write pretty much every electron configuration that you would come across. Any questions on that there? So let us write maybe some of these and see how this works. So again, here's a picture from your book of the different orders. And again, if you follow that kind of zigzag thing, it will do it for you. It's a good way to do it. So let's talk about writing electron configuration and really what it is. When we write electron configuration, it's basically the filling order of how the electrons populate an atom. And that is how you should write it. And I say that, and we'll talk a little bit about it maybe in a bit, but there is also electron configuration based on energy, which nobody really uses unless you're taking a specific class. Pretty much in all your classes that you take, you should always write electron configuration in the filling order, which is that chart we just made. And that'll put you everywhere that is correct in terms of how to do it. The number of electrons that you have in an atom, if it is neutral, as we talked about, should equal the atomic number, right? So the atomic number is number of protons. And if it does not have a charge, then that'll also tell you the number of neutrons. So you can use the periodic table to figure out how many electrons there are if you're writing electron configuration for something that's neutral. So let us start with that. There's our chart again. So again, when we look at this chart, we always want to start up here. So the very first orbital we're going to hit is this one, and that's going to start with our friend hydrogen. Hydrogen has one electron, so its electron configuration would be what is referred to as 1s1. I'm just going to write it towards the top here, so hopefully everybody can see it. Once again, as we were talking about earlier, this very first one is the principal quantum number. That is that n number, like that n equals 1. The letter that you see here is the orbital, our subshell, that we find the electrons in. And the very top number, the superscript on top, is the number of electrons in the orbital, our subshell. And that is how you say it as well. It is called 1s1. And it should look like that. It should be like a normal sized number to begin with, lowercase letter, and it should be a superscript 1 up on top. There's no dashes, there's no commas, which people like to, for some reason, put when they're doing electron configuration. There's really none of that. Yeah.
That Z.
The Z is the atomic number, like we talked about in previous chapter. So that's the atomic number from the periodic table. That is your number of protons, which in this case would also tell you your number of electrons since it is neutral, right? So again, you can use the atomic number from the periodic table to figure out the protons. And again, if it's neutral, it should have the same number. So this is the electron configuration 1s1. We could also represent sort of electron configuration by what is referred to as the orbital diagram. And the orbital diagram is either a line to represent an orbital, or sometimes people will use boxes. So sometimes people will use boxes as well. So either way. So for example, here, this would be like our 1s orbital. And we use arrows to represent the electrons that are in that orbital. And whenever you have an orbital, the very first arrow actually goes in the upward direction. So I think that was a question earlier, maybe how they go in. They actually do always go in the upwards direction. Now, just to talk a little bit again about quantum numbers, that fourth quantum number is what is known as the spin quantum number. And electrons are affected by electrical field. They have their own spin. And spin quantum number can actually have a value of plus 1/2 or minus 1/2. So that is like the two only values that an electron could have. Typically speaking, when you put the electron into that orbital, it should always be pointing up. And that is what is sometimes referred to as having plus 1/2 spin for the quantum numbers, like the upwards direction. It's important for a reason we're going to get to in just a second, and then we won't talk much more about it in just 1 second. So those are two representations of electron configuration, just writing the electron configuration, 1s1. Or if you're asked to draw the orbital diagram, it should either be lines or boxes and arrows to represent the electrons. when you're asked to draw the orbital diagram, do not just draw a picture of an orbital. It's actually talking about this with the arrows and the lines and stuff like that. Any questions on that there? All right, so let's continue on and talk about the next one, which is helium. But before we talk about the next one, let's talk about what happens with our electrons when they go in there. Now, we already, with hydrogen, as we just saw there, I'll just make a box on this. We already have basically one electron in there, and that is plus 1/2 in terms of its spin. Now, we have really two options as to how to put our next electron in. We could either put it in facing the same way or heading in the same direction, or we could put the next electron in heading in the opposite direction. So those are our two sort of options as to where we could put our next electron in there. There's actually a rule that tells us which way we should do it, and that is what is known as Pauli's exclusion rule. And basically what Pauli's exclusion rule says is no two electrons can have the same four quantum numbers. So that's like that N we were talking about, that L, that M sub L, and that M sub S. So basically what that means is if I were to put the electron in this way, where they're both heading in the same direction, they would actually both end up with the same four quantum numbers. And just for purposes here, and again, you don't have to figure out the quantum numbers or anything like that, but just to illustrate you could trust me when I tell you that if you did the quantum number for this electron for a 1s orbital, it would have a value of n is equal to 1. L would equal 0 because, as we talked about, 0 is an s orbital, so it's hanging out there in the s orbital. M sub L, it's hanging out in the only s orbital available, which is 0. And the spin for this guy would be plus 1/2. And those are the four quantum numbers for this electron. Now, clearly, this electron is pointing in the exact same direction, which means if you did it for this guy, you would also get an n equals 1, an L that equals 0, an M sub L that equals 0, and an M sub S that equals plus 1/2. Those are the exact same four quantum numbers. This would violate what is known as Pauli's exclusion rule. You cannot do that because they all have the same numbers. So basically, the way we get around that is we do not put them in the same direction when they go into the orbital. The next one coming in actually has to be going in the opposite direction, heading downward. And if we did the quantum numbers for this guy, if this was again a 1s orbital, that would be n is equal to 1, L is equal to 0, M sub L is equal to 0. So you might be thinking, those are pretty similar, all three of those so far, right? And you would be right. But the difference actually comes in the spin of the actual electron that's in the orbital. Because that one is going downwards or pointing downwards, I'll go down here, the M sub S for that guy is actually negative 1/2, which gives it not the same four numbers as the guy over here, which is these numbers here. So it's just that difference in the spin and the orientation of the electron within the orbital that allows it not to end up with the same four quantum numbers, and that will not violate Pauli's exclusion rule. So basically what that means is whenever you're putting the first electron into an orbital and you need to draw like the orbital diagram, and really how it goes in is it will always go in the upwards direction first, the first electron, and then if you need to put the next one in, it will go in the opposite direction. That will allow it not to violate basically Pauli's exclusion rule. Any questions on that? And again, you're not going to be required to figure out the L, the M sub L value, the M sub S value. Just showing you that's really the basis, for why it doesn't violate it. So with that being said, let's actually see where that occurs. First time that occurs is actually with helium. Helium, it will have two electrons, right? Because its atomic number is Z is equal to 2. We would again start up here. We always start up here. That rolls us to our 1s orbital. And we're okay because in this case, it would be 1s2 in this case for helium. Would be our electron configuration. When we come over here and do our orbital diagram for helium, we would have one line or one box that represents our 1s orbital. First electron would go in upwards. Next electron would go in downwards, right? So we do not violate Pauli's exclusion rule. Can I put any more electrons into that s orbital at this point? No, it is full, which means when we get to our next guy, we now need to zig back, right, and come to our next orbital, which would take us to here. By the way, this sort of orientation of those electrons where they're going in an opposite direction, this is what is sometimes referred to as paired spin. They basically cancel each other out. One's going a half plus a half, one's minus a half. They're pairing off and sort of canceling out their spin sort of properties there with each other. Any questions on that there? So never in the same direction when you're putting arrows in the same orbitals. They always got to go opposite. And again, they always got to go up first, down second. And again, you do not need to fill the orbital like we saw with hydrogen. You can have just one in there, for example, but any individual one could only have a maximum of two. Any questions so far? All right, let's continue on here then. Let's talk about the next one, which is lithium. And lithium is number 3, which means it has 3 electrons. And once again, if we come back to our chart here, we're again going to start up here. So we know we are definitely going to use that. That's going to take care of 2 electrons. Once again, we're going to zigzag back. And now we do need to incorporate this one as well. And that will give us an electron configuration for lithium of 1s2, 2s1 in this case. So once again, you can see there's no dashes, no commas. That is the way that you write it, just straight out like that. Once again, if you count up the top numbers, that is 2 and 1. That's a total of 3 electrons that we've now put into this atom. Again, working from lowest energy to next lowest energy, right? And kind of working our way up in terms of energy. By the way, at this point, how many electrons are on the first energy level? Yeah, and how many are on the second? Yeah, so we got 1 on the second energy level, 2 on the first. The 2 on the first are closer to the nucleus, right? The 1 on the second is a little further away. If we were going to do our orbital diagram for lithium, we need a line or a box for the 1s, and we need a line or a box for the 2s. To be truthfully honest with you, if you were to do this diagram correctly, energy goes up, so you should put them on top of each other, but just for sake of not rolling too low, I'm just going to go side by side. But technically speaking, if you're going to kind of do it based on energy correctly, your 1s would be here, and then your 2s obviously would be above it. But I'm just going to kind of go side to side so I don't run out of space and it's not too low for you to see. So in this case, we would go our first one up, our second one down, and now when we get to our 2s, we should put 1 upwards in that direction. I could put how many more electrons in the 2s orbital now? Yeah, only 1 more until it's filled, right? So let's continue on then and do that. That's going to bring us to beryllium. So beryllium is number 4 in the periodic table, which means it has 4 electrons. Again, we come back to our chart, always starting up here. We're going to hit our 1s like we did. We're going to zigzag back. We're still going to go here. And at that point, we should be good on this one. So that's going to give us, for beryllium, 1s2, 2s2. I now have how many electrons on the second energy level? Second energy level has 2, and the first still has 2. And that makes sense because we calculated in class the maximum number of electrons on the first energy level is 2, right? So we maxed out the first energy level, which means we need to go to the second energy level. That would get us, in terms of beryllium, again, we would need our 2 boxes, our lines, up, and down in this case. Any questions on that there? Again, electron configuration on the left there, orbital diagram on the right. Yeah.
Want us to like write those stacked up?
I'm going to tell you, I'll probably be okay either way you do it, to be honest with you. But if you want to do it truthfully, correctly, based on showing the energy, you really should stack them. But sometimes on papers or exams or stuff like that, you're going to kind of run into other questions and stuff like that. So I'm personally okay if you just kind of go side by side. But, some people might mark it wrong if, you didn't really kind of stack it in terms of the right energy and stuff like that. But in reality, you should kind of build on top of it and stuff like that. But I'll take it no matter which way you kind of do it, as long as the order is correct. Other questions? Okay. So then let's get into what's happening at this point, right? If we go back at our chart, we're obviously here and we can't put any more electrons into our 2s, right? So if we needed more electrons, we would need to zigzag back and now end up at the 2p subshell at this point, right? Because our p has 3 different orbitals that make it up, right? So that happens obviously at the next guy, which is number 5 there, which is boron. So let's take a look at boron. Boron's number 5. Again, we're going to start like we talked about there, here. And we got to go through here. We got to zigzag go through here. And now, as we just said a second ago, we got to go to our 2p. So our electron configuration at this point for boron would be 1s2, 2s2, and now 2p1. And in this case, how many electrons do I have on the third energy, our second energy level now? I do have 3, right? And I have 2 on the first. So that is 1 and 1 there. That's 2 and 1 is 3 on the second energy level. And obviously R2 here on the first one. Somebody buy that? Can you just hit the mute button maybe on that pad? Should be to the right. Should say mute towards the top. On the far right top pad. Just press it. All right. I maybe want to do the experiment so that fume head goes down. All right, so we do our orbital diagram here, right? So we're gonna go with our boron. Hopefully they'll repower those things back up. Now, when I get to the P, right, there are 3 orbitals in that subshell, so I will need 3 boxes or 3 lines, each to represent, for example, our px, py orbital, and our pz orbital, right? So here we're going to go up, and down, and we're going to go up in this case here. And now we have our 5 electrons field. Yeah. It does. It's a good question. Actually, the way typically that you do it is you go left to right. And that's kind of the order you remember all those orbitals that had multiple types of orbitals like px, py, and pz. They're actually in these orbital diagrams. They kind of go like on left to right in terms of how there are. So we usually feel it left to right in terms of where it goes. So it should always go on the guy on the left there to start with. Yeah.
Do we have to write the PY and PZ?
You don't for me, but you do need to write the 2p. Yeah. But just to indicate again that each of those, and again, just to touch upon that quantum number stuff we did, each of those represents those numbers that we saw, like -1, 0, and +1. And that's what each of those orbitals basically represent. In this case, obviously, we could put how many more electrons in that 2p subshell before we're full? Yeah, we could put 5 more for a total of 6. So we could actually fill this up without having to go on to the next one. So let's talk about when that happens there, which is obviously number 6. And we also have, in terms of number 6, another important rule as to how the electrons go into those orbitals. So when you come across a situation like we have with our 2p, are any of those orbitals that have subshells, so P, D, and F, right? Those are all the ones that have multiple orbitals that make up a subshell. There is a rule of how those electrons should go into these orbitals and how they should fill each other. So Hund's rule says that the most stable arrangement for electrons in a subshell is one that maximizes their parallel spins. So what is parallel spin? Well, we know paired spin, right, is opposite like that, right? So that's paired. So parallel spin means everybody's heading in the same direction. So what that means is we have a couple of options in terms of how we could fill this. We already have an electron here. We could go this way, or our other option would be to go this way. And obviously, if we went this way first, we just paired the spin, which kind of doesn't help with Hund's rule. So we do not do that. So when we have subshells that have multiple orbitals, the way we can maximize parallel spin, and you might have seen me the way I've been filling in the electrons, right? I kind of go one at a time and then come back and pair. And that is the proper way to do it. So to maximize the parallel spin, say in a P subshell, you would actually go everybody heading in the same direction first, left to right. And at that point, you have no more options. You then would come back left to right and start pairing them off. So you would come back left to right and then start pairing them off. So this happens with p orbitals because there's 3 of them, happens with d orbitals because there's 5 of them, and it happens with f orbitals because there's 7 of them. So on those subshells, if you're drawing the orbital diagram, they should always go left to right one at a time till you run out of orbitals. Then you should come back and start pairing them off left to right based on, again, how many that you need. Any questions on that there? And by doing that one at a time and then pairing off left to right, you're still keeping the maximum number of electrons going in the parallel direction, in the same direction. So that happens, like I said, at number 6, which is carbon. So carbon's got 6 protons, also has 6 electrons. And again, we're going to start here. So we got our 1s, which will hold 2. We got our 2s, which will hold 2. And we're still working through our 2p at this point. So for carbon, it would be 1s2, 2s2, 2p2. Electrons on the second energy level now is 4. Yes, they are both on the second energy level. So we have 4 electrons on the second energy level. Still our maximum number of electrons here on the first energy level, which is 2. And if we did our diagram here for carbon, again, we would have our 1s, our 2s, and obviously here our 3 2p orbitals. We would go up, down, up, down, up. And again, to maximize Hund's rule and the parallel spin, we go to the orbital to the right and put it in there. At this point, we've now put 2 electrons in our 2p subshell. We could then put another 4 electrons in there before we are filled. So let us continue on here, and that would take us to nitrogen. And nitrogen is the 7 on the periodic table, means it has 7 electrons. And that means that, again, we are still in our 2p. So we're starting here. We're good. That's 2, that's 4, and we have 6 to play with here. So we are going to then go for our nitrogen 1s2, 2s2, 2p3. Again, if you're not sure, you can count up the top numbers. 2 is 4, and 3 is 7. So we have now placed 7 electrons in here. We're now up to 5 electrons on our second energy level, 2 in the s orbital and 3 in the p orbital. For our orbital diagram, again, we would have our boxes, our lines here. And we would go up, down, up and down, up, and up in this case. Yeah. At this point, my next electron's got to go back to the left-hand side, right? And start pairing them up, right? Because we've now maximized as much as we can, getting everybody in the same direction in our p orbitals. Any questions on that there? Might as well finish out the first 10. Why not? Since, we're in chemistry class, I suppose. So we'll go oxygen there, which is number 8. So oxygen, again, would have 8 electrons. So once again, starting there at our top, 1s2, 2s2, 2p4 in this case, giving us now 6 electrons on the second energy level, 2 on the first. Our oxygen here, our 1s going up and down, our 2s going up and down, and then our 1, 2, 3, 2p. So again, up, 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 and now we come back to the left, and now we're going to start pairing it up there on the far left-hand side. Any questions on that one there? All right, then continuing on, number 9 is fluorine in this case. So fluorine, number 9 on the periodic table, meaning it has 9 electrons. And again, starting at our top there, 1s2, 2s2, 2p5, giving us now 7 electrons on the second energy level, 9 total with the 1, 2 on the first. And for our diagram here, our p orbitals here. Up, down, up, down, up, 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 and now back, down, and again, down in this case. Yeah. As you can see in the picture here, we have a spot for just one more electron, right, before we would have to move on. So again, might as well finish out the first 10 here. That's going to take us, as we super zoom, into neon. And neon's going to be number 10. And again, continuing on with our pattern here, 1s2, 2s2, 2p6 there. And that gives us, we just count up the top numbers, 2 is 4, and 6 is 10 electrons. And our orbital diagram, again, taking a look at it, up, and down, and again, our 3 for our p, up, up, and now down, down, and down. We are obviously now filled up our p subshell. So if we look at our chart, we've started here on all this, and always there's that. We zigzag back. We zigzag there. Next one that we would need is the 3s, right? If we needed to, right? To get there. Any questions on that so far? Yeah. Question or yeah. Okay. All right. So why don't you do argon, write the electron configuration, draw the orbital diagram, see what you come up with. Okay, so let's take a look. Again, we're going to start. So we want to do 18. So maybe I'll just do it here so we can see the chart as we're doing it here. So argon has 18 electrons. So again, we're going to start here and we're going to go to our 1s like we did before. So a little 1s2. We obviously need to zigzag back here to our 2s2. We need to zigzag back here to our 2p6. We need to zigzag there then to our 3s2. If you're not sure where you're at this point, again, you can just count the top numbers as 2 and 2 is 4 and 6 is 10. So we're at 12 electrons, right? So we still got 6 more to go. So we got to zigzag back. And again, the next spot's going to be our 3p6. And that should be the electron configuration for argon. Any questions on that there? Yeah. Because any p subshell could hold 6 total electrons. And because there's 3 different orbitals in there, so, and each one could hold 2. So that's the maximum, yeah. And that's why, again, when we get to something like d orbitals, they could hold 10 because there's 5 different ones and they could hold 10. Other questions? All right, so if we did a little orbital diagram, and again, I'll draw it towards the top so you can see in this room here a little bit better-ish. I'll try to draw it towards the top. Maybe I'll go underneath here just a little bit. That's 1s. We'll need a line for 2s. 1, 2, 3 for our 2p. We'll need a 3s box, and also 1, 2, 3 for our 3p. And again, we would go up, down, up, down. This would fill up, up, up. Then come back down, down, and down. This would go up, down. This p would also do the same, up, and then down, down, and down at this point. Obviously, at this point, if we needed to go, next spot would be our 4s, right? So that is, again, what comes after the 3p and before the 3d. So again, that's where people always make a mistake because they want to go in order. The only reason it goes in order, or you may actually sometimes see it in order, is it's based on energy. And when you never write electron configuration, usually based on energy, you write it based on filling order, and this is the correct order. The 4s would actually come first. I won't say you'll never see it in order, but it is based on energy rather than how they go into the atom. All right, so with that there, we got our electron configuration. Let's talk about a couple other things here with electron configuration. And that is the idea of the off-ball principle. The off-ball principle is the idea that atoms add protons one at a time to their nucleus in this sort of buildup, and electrons are added again to the atomic orbitals. A reminder, the atomic orbitals are what we've been talking about, the s, the p, the d, and the f. They are added one at a time. Again, lowest energy to highest, right, is how they go into the atom. Now, for example, if we look at potassium, which is number 19 on the periodic table, and that means potassium actually has 19 electrons. And if we were to write the electron configuration, we would have 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Again, coming to our 4s next. And that would be our electron configuration. If we look at this electron configuration, by the way, and we look at this part of it here, that is how many electrons? It is 18 electrons. If you count up all the top numbers, that is 18 electrons. If we go to the periodic table and we look at number 18, which we just did electron configuration for, who's number 18? That's argon's configuration, right? So there actually is a shorthand that is sometimes used with electron configuration. And that shorthand is sometimes written like this. You would put in brackets argon to represent its configuration. And then you would just continue on with the electron configuration. So this is what is sometimes referred to as argon 4s1. It's how you say that. And that's sort of like a shorthand for electron configuration. Argon is what element on the periodic table? What type of element? It is in which group? It is a noble gas. And that is what needs to go in the brackets. So inside the brackets there, it needs to be a noble gas. Sometimes it's called noble gas configuration. Sometimes people call it. But it needs to be a noble gas. And it should always be, if you look at the periodic table, it should always be the noble gas that comes right before whatever element you're trying to write it for. So whichever one comes right before it. Yeah. Yeah, it's always got to be a noble gas that comes with that. So for example, if we looked at sodium, for example, sodium is 11 electrons. It's number 11 on the periodic table. If we just write the electron configuration for sodium, it'd be 1s2, 2s2, 2p6, 3s1. Once again, if we take right before there, that set of the electron configuration, that is 10 electrons. And if you look on the periodic table, that is our friend neon, and it would be 3s1. So if you look on the periodic table, if you go back one from sodium, it's neon, and that is the noble gas that comes right before it. So it does always has to be a noble gas that's in there. And then you basically just kind of continue on with the configuration as needed. Yeah. Any questions on that there? Yeah.
Why better to write it short kind of way versus like that?
There's really not, other than it takes up less room, obviously, and stuff like that. So there's no real reason, except as you continue on, the electron configuration get larger. So sometimes people like to do sort of a shorthand, so as they're writing it down, it's not, so long and stuff like that. So you could do it either way. If I don't ask you, or if I don't tell you not to do it, you could do it either way. But if I tell you don't use noble gas configuration, then write it the long way, if you will. But if I just say give me the electron configuration, technically you can do either one, and they are correct, as long as you do it correct, obviously, the shorthand part of it. Yeah. Other questions on that? Now, let's talk a little bit about transition metals. And transition metals are kind of confusing a little bit, if you will. But transition metals actually is where we get into those d orbitals. So transition metals on the periodic table is pretty much where you're going to hit those d orbitals. And remember that the order, right, in terms of energy, is we have our 4s orbitals, and then, for example, we have our 3d orbitals in terms of energy. So as the electrons get into those transition metals, we are going to fill the 4s first, but then we're going to fill the 3d with electrons. So there's actually two exceptions in the transition metal region that if you follow the sort of zigzag way that we've been doing, you will get sort of the incorrect electron configuration. Truthfully, there's actually more, but the two that you need to know is chromium and copper. Chromium is number 24. Copper is number 29. So they have 24 and 29 electrons respectively there. if you were to follow your zigzag guy, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And if you did it for copper, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. So the exception for these two actually happens at the very end here. So it's these guys right here. And it is between the s and the d orbitals where the exception sort of happens. And it is because, in terms of energy, these sets of orbitals are really, really close in energy. They're super close in energy. And as we'll talk about in a second, actually what happens when you put electrons into the d orbital, they actually switch in terms of their energy levels. So the Ds actually drop lower in energy than the S's when you actually start filling them up. But before then, the S is lower than the D. And because they're so lower than D, it's been found experimentally that they are more stable with an extra electron kind of pushed up into the d orbitals. And in the case of chromium, we put one more electron here, one less in the s, and it's the same exception. So you can see on the bottom there, or maybe you can't, depending on where you're sitting, but I'll write it up here on top. We could shorthand this up through basically this part. That's argon, which is our noble gas that comes before chromium or copper. And for chromium, it's 4s1, 3d5. So what that essentially does for chromium is it maximizes a lot of parallel spin. Right now, everybody's heading upwards, and it will maximize the parallel spin. For copper, it's pretty much argon 4s1, 3d10. That also balances out fills up the d orbitals and makes it more stable. So for our class, and probably most of the chemistry classes you take, maybe 1A, they might want you to know a little bit more, but those are the two exceptions to the normal electron configuration. I'll be honest with you, if you look on the periodic table, or if you have one in front of you, if you look on the periodic table where like those two guys are, you got like chromium there, and then a little bit down the road, you got copper. And if you come down on the periodic table and kind of in below them, there is a lot of very similar exceptions. For example, like silver is an exception. PD is an exception. Actually, with PD, there is no electrons in the s. They have all jumped up to the d orbitals and stuff like that. So there's actually a lot of exceptions in terms of where those electrons end up if you kind of go below those two on the periodic table and in. But for us, we're just going to worry about those two, which is chromium and copper. So you're expected to write the correct electron configuration for those, which is basically what we see here and not what we see up there. An extra electron up in the D, one less in the S. For all the other ones, even though they're realistically speaking, they are exceptions, like silver and all those, you could just follow the zigzag for our class. Later on, again, if we take 1A, they may want you to know those as well, but there are definitely more exceptions. Any questions? And online as well, they might have it as the actual exception. So just keep an eye on that. If it's below chromium or copper, it could be one of those exceptions. I don't think online they'll deal too much with those. But for us, you could write them like normal. These two you need to write correctly and stuff like that. Any questions on that? So as I was saying, with our d orbitals, what actually happens is, in terms of energy, they are very close. And once you start actually populating the d orbitals, as I mentioned, they actually do switch. And it ends up being that the 4s orbitals actually ends up, after they've been filled, with the d orbitals have been filled, as actually being higher in energy. And that's really important as we'll talk about what happens when, say, they lose electrons and stuff like that. But there's actually that switch in energy that actually occurs. This is also why I mentioned a second ago that sometimes you will see people write electron configuration like all in order. They'll do like, 3s2, 3p6, 3d4, and then 4s. And the reason they do that is it's really based on energy rather than filling order. And we don't do that in this class or pretty much any chemistry class you take. So again, filling order, like we talked about with that zigzag thing, is typically the way that you want to do that. Any questions on that? We'll get to that in just a second as well. Now, again, here's a list of some of those other exceptions. As I mentioned before, you are responsible for chromium and copper. But again, you can see, or maybe again, you can't see down there, but PD, for example, actually has no electrons here in the s orbital. They've all been jumped up there to the d orbital. So there's a lot of exceptions. They're all mainly in the periodic table in the same location, kind of below those two and in. But for us, again, just the chromium and the copper are the two you'll be responsible for, and it should be written like it is there on the right-hand side. Okay. All right. Now, the lanthanide series and the actinide series, those are the guys, the two rows on the bottom of the periodic table. That's actually where the Fs actually start to come into play. And that's where we start to see our F orbitals happen. And remember that the F orbitals don't start until the fourth energy level. So that's why it's 4F and 5F is where we get there. And as you can see, that's kind of the bottom of the periodic table. So we're kind of out of numbers at that point, which is why, again, we don't get into like those G's and all that type of stuff. We don't really need them for anybody that's on the periodic table. So again, through F, we'll basically take care of everybody that's on the periodic table that you need. And again, just to show you, maybe here, if I get it up, show it there. Again, you can see a lot of those exceptions. There's our exception, exception, exception. Again, there's a lot of them, you know, in this region around here, underneath those guys. And again, here's another exception as well. So let's talk a little bit about the periodic table and electron configuration. If you know what you're doing, you can actually just count off electron configuration off the periodic table. And you can do that by using the periods here. So the periods are actually the n numbers. So that period 1 is n equals 1. This would be like n is equal to 2, n is equal to 3, and so forth. So when you look at that, there are group 1 and 2 on the periodic table. This is what is known as the s block. And how many electrons can you put in an s orbital? 2. That is 1 and 2. Yeah, 2 electrons. Yeah. Groups 3 through 8 is the p block. And if you fill up the p subshell, how many electrons? P, you could put 6 if you fill up the subshell. 1, 2, 3, 4, 5, and 6, basically. The transition metals in the middle are the d subshells. And that is where you could do 10 if you fill them all up. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And our two guys on the bottom there, maybe I could bring it up a little bit-ish. Our two guys on the bottom here is our F subshell, which you could do 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. You basically could literally just count it off. Again, if you know what you're doing. So you do want to be careful. So just to show you, for example, if we look at sodium, which is right about here. So if we were to count off the electron configuration for sodium, we would start here. This is 1s1, which is hydrogen, all the way down to our helium over there, which is 1s2. That's 1s2. We would come back here. That is 2s2. That is now 2p6 all the way to the end. And now that is 3s1. There's the electron configuration. If we went to chlorine, which is right about here, again, we would start up here, 1s2 to the end for chlorine. 2s2 to here. 2p6 to the end. 3s2 to here. And now 3p, 1, 2, 3, 4, and 5. Yeah. I guess squeeze that in there badly. So 1s2, 2s2, 2p6, 3s2, 3p5. Yeah. Now, what happens when we blank the screen? It goes so you can't see it. That's what happens. So let's say what happens if we get over here, though. Let's just do our friend. Should do iron, which is right about here. That's about iron. So if we were to do iron and count it off for iron, we go 1s2 to here, 2s2, 2p6, 3s2, 3p6 to the end, 4s2. Remember, they come first. And now this is what D here? This is actually 3D here, right? Because it's on period 4, but Ds don't start until the third energy level. So that's actually 3D. 3D 1, 2, 3, 4, 5, and 6. 3D6. It is not 4D, right? So D's are actually one behind the period number. Yeah, that's 4D. This guy here is, well, I'm sorry, 4D. This guy here is 5D and so forth, 6D as you go down. So it is one behind the period number, the D. By the way, the F's, which are on the very bottom, which hopefully you can kind of see, hopefully, depending on where you're sitting, they technically go right there into here. But F start actually at 4F, and this is 5F. So they are actually two behind the period number as well. So it gets a little crazy if you do not know what you're doing. You may go wrong in terms of counting. So I would recommend maybe just following the zigzag way. You'll be in good shape. You can use this to test or check yourself, but it does, you got to be careful there when you get into the D's. You also, when you get down to the F's, need to be careful as well in terms of the numbering as they are two behind. So again, the D's there are one behind the period number, and the F is two behind the period number. Any questions on that there? All right, why don't we take a little break and come back? So why don't you take 10, 15-minute break and come on. Okay, any questions so far on what we've been talking about? So obviously you need to be able to write electron configuration, you need to be able to do the orbital diagram. Again, probably if I put that up there, it might be better as well. There we go. You also, again, can use the periodic table. Like I said, I would probably use the zigzag sort of approach just to make sure you don't make a mistake. But again, you could also just go off the periodic table and maybe double check yourself. So if we had something, for example, that did have a charge, so let's just say we talked about sodium there, and sodium with no charge, which is 11 electrons, would give us our 1s2, 2s2, 2p6, 3s1. Now, when sodium does make a charge, it will be +1. And as we talked about, basically what that means is it has lost 1 electron, and it will actually have 10 electrons in this case. And if we were to write the electron configuration for the ion that is sodium, it would be 1s2, 2s2, 2p6. By the way, that is 10 electrons. Who on the periodic table is 10? That is neon's configuration. So we'll have the same electron configuration as neon. If I look at something, say, like oxygen, which again, if it does not have a charge, has 8 electrons like we saw earlier, 1s2, 2s2, 2p, ahead of myself there, 2p4 would be 8. When oxygen makes a charge, it is a -2 charge, and that is 10 electrons, which means it would have 1s2, 2s2, 2p6, also neon's configuration. So neon, oxygen with a -2 charge, oxide, and sodium with a +1 charge, they all have the same electron configuration. That is what is known as being isoelectronic with each other. They're isoelectronic, same electron configuration. By the way, oxygen gained 2 electrons and ended up at neon's configuration, right? And sodium lost an electron, went backwards on the periodic table to neon's configuration. They both end up with noble gas configuration. Noble gases are chemically inert, they're really stable. That is really the purpose why they gain those charges, so that they end up with the same electron configuration as a noble gas, which makes them really, really stable in that sort of situation. So that's really the basis, as we'll talk about in the next chapter, which is bonding, why an ionic bond happens. Metals typically will lose electrons, and they will back up on the periodic table to the noble gas that comes before them in terms of their electron configuration. Metals will gain electrons and go forward on the periodic table to the noble gas that comes after them to get to that really stable configuration. As we'll talk about in that next chapter, pretty much that's the whole purpose of all bonding, is for everybody to end up with the same electron configuration as the noble gases, because they're really, really stable. Just so we're clear, they do not become those noble gases. So sodium with a +1 charge or oxygen with a -2 charge do not become neon. They don't become neon because what doesn't change? Yeah, the protons stay the same. So they're still those elements, but they do become the same in terms of how their electrons are at that point, which makes them really, really stable. So that's, again, an important thing to remember. So when something has a charge, you do have to adjust its electron configuration, either add more electrons or take away electrons when we do have a positive charge. Transition metals, which we'll save maybe for next time, they also make charges, but their electron configuration is a little bit different. So I do want to get to some other stuff right now. So we'll come back and talk about what happens with transition metals, and we'll do a couple more examples of things with charges as well. So what we want to kind of finish up talking about in this chapter is sort of periodic trends and a couple important things that happen in terms of the periodic table and electrons are, first off, in terms of bonding, valence electrons. Valence electrons are the electrons that are involved in bonding. They are the highest energy level electrons. So the example there, right up on top so you can see it maybe a little better, is nitrogen. It has electron configuration 1s2, 2s2, 2p3. As we talked about, it has 2 electrons in the first energy level. It has 5 electrons in the second energy level. These are the valence electrons, those in the outer energy level. The ones in the lower energy level, they are sometimes referred to as core electrons. They are closer to the nucleus. They're held tighter. That is why valence electrons are actually what we use in bonding, because they're not as close to the nucleus, they're not held as tightly, and they're able to participate in bonding. Now, for example, if we took oxygen that we just did, which would be 1s2, 2s2, 2p4, these are both in the second energy level. 4 and 2 is 6 valence electrons and 2 core electrons here. So you could absolutely write the electron configuration, and basically all the electrons that are in the highest energy level will be the element's valence electrons. Or you could just do the much simpler way, which is the number of valence electrons actually equals the group number. So the number of valence electrons for an element will equal the group number. So if you look at nitrogen that we just did, it is group 5, and it has 5 valence electrons. I just did oxygen, which is right next door. It is group 6 on the periodic table. It actually has 6 valence electrons. So you could do the group number there. Sodium, group 1, has 1 valence electron. It will equal basically the group number. Now you may be asking, what about like our transition metals? Well, they are a little different in terms of valence electrons, but they also go by the group number. So for example, and I'll just do like iron right here, right? And if you count iron, it is technically, it'll come up this way. We have group 1, group 2, and then we do the kind of 1 through 18 numbering in this case. This would be group 3, 4, 5. I totally did that, not so great. 6, 7, and we'll spread it out there, 8. So iron would actually have 8 valence electrons. And if you look at iron's electron configuration, that would be argon 4s2 3d6. Right here is the 8 valence electrons in the transition metals for iron. Transition metals have basically more valence electrons because they have the S's and the D's that are considered valence electrons in that case. And in this case, that would be the 8 valence electrons there for our iron. So if you're looking at transition metals, you actually want to just kind of do the 1 through 18 numbering, starting left to right, and whatever group it's in would be what it is. For example, zinc at the end is technically group 12, and it would have 12 valence electrons. So valence electrons for transition metals are a little bit different, and that's why when they make charges, it's a little different where they come from, how they get to those charges, and we'll talk about it. But they have the availability to them, transition metals, all of the s electrons to use, like for valence electrons, and all those Ds as well. So they could have upwards of 12 up here. Yeah. They do go back, yeah. So you kind of want to use, I guess I should say 1 through 18. You kind of want to go use kind of the 1 through 18 for just the transition metal numbering. But you're absolutely right when you go past there. So when we come back over here where like boron is and all that good stuff, you then want to drop back to 3, 4, 5, 6, 7, and 8 as you go through there. So yeah, so for our representative elements, not in the transition metal region, you want to use that A numbering, the 1 through 8, and that will give you the proper number of valence electrons. But definitely for the kind of transition metal, you want to kind of go 1 through 12 basically, and kind of number it that way. Other questions, or was that your question? Yeah.
Why did you put argon and then that? Is it like I know that argon is like a noble gas, but it's not like right before Fe.
It is. It is the noble gas that comes right before iron if you back up.
Oh, so it's exactly right before?
No. So when we talk about right before, when you look on the periodic table, it has to be the one that comes right before you get to that element in terms of noble gas. So all the noble gases are over here in group 8. So it's got to be whichever one of these comes before you get to, that element. Yeah. Not the one that comes after it when you do that. So, yeah. Other questions? Okay. So let's talk a little bit about metals and non-metals. Metals, as you go down a group, especially group 1, they tend to give away their electrons a lot easier. And cesium, rubidium, potassium, sodium, and lithium, it kind of increases as you go down the group. And that's because those electrons are further away from the nucleus. They're not held as tightly, so they're easy to be given away. Non-metals, on the other hand, are upper right of the periodic table. So as we're going to talk about some periodic trends now, and basically what you will see is upper right of the periodic table is where you find your most reactive non-metal. Lower left of the periodic table is where you find your most reactive metal. And for these reasons we're going to talk about here. So really, in terms of reactivity, we kind of see those extremes. Remember, nonmetals are up here to the upper right of the periodic table, right? So upper right, your most reactive nonmetal. Lower left, your most reactive metal. So let's talk about some of these trends. The first sort of trend is what's known as effective nuclear charge. It is sometimes abbreviated as Z effective. And the easiest way to sort of demonstrate sort of what effective nuclear charge is we'll just look at one like lithium. Lithium has 3 electrons. And if we write our electron configuration, it is 1s2, 2s1. By the way, lithium is group number 1, which means how many valence electrons does it have? Yeah, and it's this guy right here, right? That is the valence electron for lithium. So if we were to look at lithium, it has a +3 charge for the nucleus, right? And that's from the 3 protons that it has. And on the first energy level, I'll just draw it like this. We have a couple of electrons, right? These guys here, these are the core electrons hanging out there on the first energy level. On the second energy level, we have, again, our randomly moving electron there in the second energy level. Now, what happens in a situation like this is these electrons here are core electrons. They essentially feel the full brunt of that positive 3 charge. And if you remember, I think we talked about it, that when a positive thing and negative thing come together, the higher the positive or negative charge is, the stronger they're held together, right? So the larger the charge, the stronger that opposite attraction is going to be. So those two electrons, which are flying around randomly in that lowest energy level closest to the nucleus, is going to be held really, really tightly by that +3 charge. What happens, though, to our poor valence electron that's hanging out here, our valence electron, is it actually is experiencing what is referred to as shielding by those lower energy level electrons. So the outer valence electron is actually not feeling the full brunt of that +3 charge. It's like if you went to the movie theater and you could pick your seat years ago, I suppose, and you got there early, you got the seat right in the center of the movie theater right before the movie starts. Somebody comes and sits down in front of you with a big giant cowboy hat and blocks half of the screen, right? He's now shielded you from half of the screen that's there, right? And that's what's happening here with those lower energy electrons. They're shielding that valence electron that's flying around from the full brunt of the positive charge. You could actually calculate what it is feeling. So the Z effective is basically the atomic number of protons, which in this case would be +3, plus basically the number of electrons that are shielding it, which in this case is 2, so plus -2, which means that outer electron is not feeling a +3 charge. It's effectively feeling only a +1 attraction, which means it's not going to be attracted as strongly as those core electrons. That's also why that valence electron can be popped off and used in sort of an ionic bond or anything like that, and is lost because it's not being held as tightly as those core electrons. Those core electrons are being held super tightly. Good luck trying to rip those off. Not going to happen because they were just feeling that full brunt of it. So electrons that are in lower energy levels will actually shield electrons in higher energy levels. And that's how we get to our valence electrons that are actually involved in bonding, because they're just not held as tightly because they're not experiencing the full brunt of the positive charge from the nucleus that those lower energy electrons are. Electrons on the same energy level don't shield each other. It's just ones on lower energy levels shield them. So in terms of the periodic table and trend, when you look at Z effective, it actually increases as you go this way on the periodic table, and it decreases as you go this way on the periodic table. So that's one really important sort of thing. If you think about it, as you go to the right on the periodic table, you're now going to have a lot more electrons, right? The atomic number increases as you go to the right, which means the electrons in the nucleus is going to be a lot more. I'm sorry, the protons in the nucleus, not electrons. The protons in the nucleus is going to be a lot more. You're going to have a greater positive charge. That's also going to cause even the outer electrons to be pulled closer, right? Because you have a much bigger positive charge than you do on the left-hand side of the periodic table, where you don't have as big a positive charge. It's not going to pull those electrons as close. And that's also why they're not going to be held as tightly as well. Any questions on that there? Yeah. Yeah.
Those are electrons not included valence electrons, correct?
This too?
Yes.
Yeah, these two represent basically the core electrons that are doing this screening, or the shielding, basically. Other questions on that? Another really important periodic trend is ionization energy. And ionization energy is the energy required to remove an electron from the gas phase of an atom. So when we lose an electron or remove an electron, you actually become positively charged. And we usually think of ionization energy as basically involving the formation of cations, right? Positively charged guys. The higher the ionization energy, the harder it is to remove an electron. The lower the ionization energy, the easier it is to remove an electron. Metals typically will have very low ionization energy, so they lose electrons really easily. Non-metals have really high ionization energy, so they tend to not lose electrons. In general, just so you know, electrons actually come off one at a time. So for example, if I had magnesium with no charge, it would lose one electron. And we again could represent this with this type of reaction where we see the electron on the product side like it's being given off. And by the way, to do this, this would be what is known as the first ionization energy. That is the energy basically to pop off that first electron. Next will happen is the magnesium with a +1 charge will lose a second electron. Again, this would be the second ionization energy. And then maybe what would happen is magnesium that's already lost 2 electrons may lose a third. Let's kind of write it over here so if we can see it. And that would be the third ionization energy. If you had to take a guess, which one is easier to do? If you lose the first electron or, say, the second electron? Which one should be easier? It's actually easier to remove the first electron. When you remove the first electron, does the size of the ion get larger or smaller? Electrons are flying on the outside, so you lose an electron, the whole thing shrinks, right? You lose some electron cloud, basically. So when you lose those electrons from the neutral atom to the positive cation, it gets smaller, basically, as it loses those electrons. What does that also do? As it gets smaller, it moves those outer electrons now closer to the nucleus, right? And now they're closer to the nucleus, which means it's going to be even harder to try to remove the next one, right? You remove the next one, it gets smaller again, right? So every time you remove an electron, you're actually moving those electrons that are left closer to the nucleus, which means it's harder and harder to remove extra electrons. And at some point, it may not happen. So as you compare, for example, the first ionization energy to the second to the third, and so forth, it actually starts to increase as you go from the first to the second to the third. So every time you lop off an electron, it takes more and more energy to remove the next one. Any questions on that there? Yeah. I'm going to answer that question in maybe a slide and a half. Okay. Yeah. All right. So again, this is the general trend on ionization energy when you look on the periodic table. It increases as you go up and to the right and decreases as you go down. So for ionization energy, this is first ionization energy. It increases up to the right and decreases down. Now, to answer your question, this table will probably help us maybe answer your question. So for example, right, we talked about basically our magnesium losing 1, and that's our first ionization energy. Our magnesium then dropping a second one, and that's our second ionization energy. And then if it continued this pattern, it would drop again like we saw in the last slide there, a third one, and that would be the third. We could see on this chart here, if we actually just look at, for example, maybe, if it lets me do it, there we go. The ionization energy as we go from first to second to third, it increases, right? The first one we could take off with 735, then it doubles, right? 1400. As you go from the second to the third, we then get a like 6-fold jump in energy needed. That's a pretty big jump. If you look at aluminum, first one 580, then it goes up, third electron 27. What happens as we go from the third to the fourth? Pretty big jump in terms of energy that happens. So what's happening at that point is this. Magnesium's electron configuration, for example, is 1s2, 2s2, 2p6, 3s2, and there it is. Number of valence electrons for magnesium is group number 2. Should have how many? These guys right here, right? So first ionization energy, not too bad at 735. Second one, a little bit more. After I get rid of these 2 electrons, which are the valence electrons, what electrons am I into now? like core electrons, right? And those started out really close to the nucleus, held really tight. You now just pushed them much closer, right? And that's why something like magnesium has a fixed charge of +2, because good luck, you're not going to do that. It's not energy efficient to do so. Also, why, like we talked about, aluminum is group 3, has 3 valence electrons, because by the time you get rid of the third electron, that fourth electron is a core electron, which is sitting fairly close to the nucleus, and it's going to be held really, really tight, and it's just not energy efficient. So that's why we talked the other day where certain things have fixed positive charge, for example, and that is because of this. At some point, you're going to hit those core electrons, and it's not going to be energy efficient to try to rip those off. It's just not going to happen, and that's why they stop at that particular point. Any questions on that there? That's also why transition metals can make a variety of charges, because they got upwards sometimes of 12 valence electrons to play with before they're in trouble, so they can make a variety of charges. These guys are kind of fixed in the number of valence electrons, that they're going to sort of gain or lose, or actually lose. The next sort of trend is electron affinity, and electron affinity is the energy change that occurs when somebody gains an electron. So electron affinity, when we gain an electron, you become negatively charged. So we think of electron affinity as things happen when we make an anion. It's actually the energy change. It is not perfect trend, but it does increase as you go up and to the right, and it decreases as you go down and to the left. It's not perfect. For example, if you look at group 7, it actually increases as you go up, and then it decreases and then increases. So it's not a perfect trend, but the overall general trend is that. That should not be confused with another word that sometimes is confused with, which is electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. And electronegativity actually increases on the periodic table as you go up and to the right, and decreases as you go down. Our most electronegative element you could have is fluorine. So fluorine is the most electronegative element that you actually could have. And it does increase as you go up to the right and decrease as you go down. And that is different than electron affinity. Electron affinity is the energy change that occurs after you gain an electron. So there is a difference in those two things. Any questions on that there? Now, atomic radius is affected by effective nuclear charge, and it actually does get smaller as you go from left to right on the periodic table. So the size decreases as you go left to right and increases as you go down. By the way, we didn't talk about it a second ago, but let's just talk about it. For our anions that are negatively charged, what happens to the size of the negatively charged ion versus the neutral? Does it get smaller or larger? It does get larger because it's gaining electrons, so it's going to build out, right? So anions, on the other hand, they actually increase in size from their neutral guy because they're getting all those electrons. Is there a question? You're good? Yeah. All right. So how does all these trends kind of come together and help us understand what happens? Here's a picture from your book of atomic size. And again, you can see it gets much smaller as you go to the right, increases as you go to the left. So let's see if I can find some place. I'm going to write it on here, I think. If we were to sort of take all of our trends together, and I'm going to try to do this on the top half so you can see it a little bit easier. As we go from left to right in terms of Z effective, it increases, and then it decreases, obviously, as you go this way. As we go from left to right here, decreases and increases ionization energy. As we go from kind of left to right and then down, it decreases and increases electron affinity, EA. As we go down and to the right there, It increases to the right and decreases for electronegativity. That. And then obviously we have size here. Decreases as you go to the right and increases as you go to the left. So when we look at the periodic table, as we go up and to the right, we have a greater effective nuclear charge, which means even the outer electrons are feeling a much stronger pull to the nucleus. And that's going to bring everybody in closer, which is why we see the size get smaller. And because everybody's in closer and the size is smaller, it takes a lot more energy if you want to try to remove an electron. They also will typically like to bring electrons towards themselves, and they also will pretty much like to accept electrons. And those are all the trends that we see as we go up and to the right here for our nonmetals. And that is why nonmetals are typically the ones that will gain electrons. They're small, they hang on to their electrons, and not only do they hang on to their electrons, they want to take other people's electrons because they have very high electronegativity. So they want to bring other people's electrons towards themselves. When we go left and down on the periodic table, we have a smaller effective nuclear charge, which means those outer electrons aren't going to be brought in as close to the nucleus. That's going to result in a much larger radius. They're going to have a much larger radius in terms of their size. That's also going to mean those outer electrons, because they're not as close, are not going to be held as tightly, which is why they have low ionization energy. And also, they are not interested at all in hanging on to their electrons, and they're not interested in taking other people's electrons, which is why they have low electron affinity and low electronegativity. So all of those trends together, when we come to the bottom left here with our metals, these are all the reasons why metals will lose electrons. They basically have all the periodic trends of take my electrons, please. I don't want to hang on to them. You take them. And nonmetals have all of the characteristics of I'm going to keep my electrons and I would like yours as well. That is why when we put a metal and a nonmetal together, we get an actual transfer of electrons. Because the nonmetal is like, I want your electrons. The metal's like, go ahead and take them. I don't care. We're good. And then we get that ionic bond that basically forms in this case. Any questions on that there? That is also why, as we'll talk about with bonding, when we do covalent bonding, which is between nonmetals and nonmetals, they both have properties of we're keeping our electrons and we want your electrons. So when two nonmetals get together, they don't transfer electrons. The best they could do is share electrons, agree upon sharing, because neither one of them want to give away their electrons. And that's why when we have a metal and a nonmetal come together, the metal is like, take it, nonmetal wants it. But when two nonmetals come together, we get more of a covalent bonding. Any questions on that there? All right. So which one should be larger, sodium or chlorine? If we look at the periodic table, they're in the same period. Chlorine is further to the right, which means it should be smaller based on those periodic trends, and sodium should be larger. Which one is the larger atom? Lithium and cesium. They are in the same group, group 1 on the periodic table. Cesium is towards the bottom. Lithium is towards the top. Remember, size increases as you go down a group. So cesium here should be the larger atom in this case. Yeah. And which one is larger, the hydrogen 1s orbital or the lithium 1s orbital? It is going to be the hydrogen, and that is because hydrogen only has one electron, right? So it is going to be by itself. When we get to lithium is 1s2, 2s2. It has two of those, right? So 1s2, 2s2 for lithium, or 2s1. There you go. And because of the presence of this guy, is going to make him kind of push in closer and not be as big as hydrogen, which doesn't have the 2s orbital, is going to be a little bit bigger. Which one's lower in energy? It's going to be lithium's 1s orbital because, again, for the same reason, it's going to have that greater effective nuclear charge, right? So it's not going to pull it in. It's going to pull it in much closer to the nucleus. Because when we look at lithium, it's got a +3 versus hydrogen that has a +1. So when we talk about our 1s orbital, it's going to be brought in closer to our +3 versus our +1. It's not going to be drawn in as close to it. All right. And I think we're good on that. What elements here have increasing ionization energy? S, O, and F. So if we look at this on the periodic table, this is what it looks like. Their positions. So we can see here in terms of ionization energy, it increases as we go this way. Fluorine should have the most. He should have the next most. And then sulfur should have the least. And in terms of atomic size, it decreases as we go this way and increases as we go this way. So fluorine should be the smallest. Sulfur should be the largest coming down here based on their location on the periodic table. Any questions on any of that there? All right. It was a big day, of lecturing.